Hi, Su Yang, are you here?
Yes, I can hear.
Thank you. Thank you for your service. Thank you so much for your time and effort. So, yes, nothing difficult. As soon as the speaker arrives, please make him or make her co-host and just make sure that this recording is ongoing all the time.
Yes. Okay.
Okay. Thank you. I will be moving around, so if something comes up, just let me know.
Okay.
Okay. See you.
Hello, do you hear me?
Hello. Yes, I can hear you very clear.
Okay, that's fine.
Yeah. Thank you so much for your contribution, Professor Ferrandi.
No problem. It was
Yeah.
it was my
Do you,
pleasure to prepare this material.
mhm. Do you see the ESWIC logo from the participant list?
Not yet.
If you look at this participant list, then you may
Yeah.
see that, yeah, ESWIC underscore AMSOP. Actually, this is our volunteer student. Her name is
Okay.
Su Yang. So if you have any technical difficulty during your class, then she will be here to help you. So if anything comes up, just let her know. And she will be also helping you when you receive the question from this Zoom chat during the class. I suppose that you do not pay a lot of attention to the Zoom chat, but if something comes up
I
as a
will try
question,
to keep an eye on the chat. Let
mhm,
me just try to understand where I can put okay, this one.
mhm,
So I have two screens, so I'm going to put the chat on another screen.
mhm.
That should work. I think that everything should be fine. Do you know how many students will attend this class?
Let me quickly check. It's like slightly more than 10, but this is based on our registration record. People sometimes change their mind and sometimes they are
Okay,
moving around. But yesterday I saw that there are no big audiences. So people know that the video will be available later on YouTube. So they decide
okay,
to, watch this video asynchronously later on.
okay.
So yeah, most probably not so many people. But after this session, we will download this recorded video and we will somehow trim out unuseful part and we will upload the video. If you need an access to the file, feel free to let me know. I will send you
Okay.
the file.
Okay.
Cool. Thank you. And
Uh, Let me share the link to the PDF so the students will later be able to download the material. So in this way, I'm going to check if the chat is working.
mhm.
So these are two links to OneDrive files.
Oh yeah. Yeah, I think this link is working on my iPad.
Perfect.
Great. Thank you so much. So, yes, we don't have any moderator here in this session, so please introduce yourself briefly at the beginning,
Okay.
and you can just directly start your lecture. Yeah, I will
Okay.
be here, so if something comes up, just let me know. But probably I will be moving around different Zoom
No problem.
meetings. So, yeah, but the student volunteer will be here to help you.
Okay. That's fine.
Thank you. Thank you so much. Thank you for your contribution.
It's been a pleasure.
Bye. See you around.
Okay, so the slides are there. I hope that the slides are fine. So let me introduce myself. I am Fabrizio Ferrandi from Polytechnic of Milan, and I've been working on high-level synthesis for a quite long time. And the today lectures will actually deal with high-level synthesis in different flavor. I'm going to present the basic of high-level synthesis or some sort of introduction of high-level synthesis. And then I dig into more complex things like how to synthesize pointers, how to call function passed by pointers, and how to deal with parallelization, and how to deal with all the stuff that are currently required in this context. Later, after this first part, I'm going to move to a second part. This second part has been prepared by Antonino Tumeo. Antonino Tumeo is from Pacific Northwest National Lab in US. And this second part is dealing with how to perform the hardware generation starting from an high-level description, maybe described in Python. So some sort of end-to-end design flow starting from a very high-level description meant for machine learning, and how this description will be translated in an accelerator that could be implemented on an FPGA or on an ASIC device. So as you have seen on the chart, you may found the link to the slides. In the slides, there are some links to other material, so you may actually found many interesting things even outside from these lectures. Just one note, the class was meant for 2 persons, so I was designed as a first part presenter, and then the second part was to be to be presented by Antonino Tumeo. Antonino Tumeo recently had very serious family problems, so was not able to take part of this class, so I'm going to manage his part and present in his behalf. Okay, so let's start. So the first part I'm going to present is very, very base stuff. So the idea is to present introduce the problem of high-level synthesis, then later to consider the idea is then to try to introduce the models associated to high-level synthesis, or sometimes is even named architecture of synthesis. Then I will try to, in a few slides, some sort of one-to-one basic stuff for high-level synthesis, present all the problems that need to be solved in order to get the final accelerator written in RTL. So let's start. So motivation for high-level synthesis. The high-level synthesis is a technology that is there for from quite some long time. So the idea, I mean, this technology was there, for example, starting from the end of the 80s, beginning of the 90s. But now it's starting to be quite mature, and it has been used even in industrial environment, and it's one of the key element in the design of complex accelerator, as you will see later. The motivation about high-level synthesis was mainly to try to simplify the life of a designer. So raising the level of the abstraction used to describe a system could be somehow simplify the work, increase the productivity, reduce the detail required to describe the application, and somehow use these kind of things in order to perform design space exploration, because you just need to change few things in the specification in order to see how this change may affect the performance of the accelerator. So those kind of, the second motivation is so the reduced design time, and the third one is related to the fact that with this simplified specification, you may be able actually to explore quite much in the design space of an application. Now, let's move to the. Let's try to describe which kind of problem we are trying to solve. So if we try to summarize in few lines what the high-level synthesis is doing, we may see that the high-level synthesis has as input a description. This description sometimes is a very high level. Consider that, for example, during the 90s, the specification used to describe an application was a behavioral VHDL. This behavioral VHDL was then translated in something that is much more structured, the one with components interacting with each other. The idea is to use VHDL or high-level language in order to remove all the burden that you need to have. You need to consider when you are describing an application with low-level component and so on. This kind of thing. So this was the time of a behavioral compiler. Just a second. So you have the behavior, a set of resources that you would like to use. And this set of resources are somehow characterized. You know how long they take, the execution delay, and so on and so forth. And then you would like to compose all those things in a single design, and you would like to do this in an automatic way. So the input are specification, you have constraint, you have objectives. As you will see later, the objective could be many. So, and you would like to generate a data path plus a controller. So something that could be easily implemented on hardware. Hardware means FPGA or ASIC. And so there are many tasks in order to accomplish this. So you need to understand when the operation need to be executed, which operation will be mapped on which resources, and so on and so forth. About the objective constraints, so it happens quite frequently that we have some sort of dual purpose for the objective. So an objective could be an objective or could be a constraint. So the design could be somehow optimized, constraining the resources or the area of the design, or you could constrain the latency and you would like to minimize as an objective the area of the design. And so you may do the same things, vice versa. Typical constraint objective are area, cycle time, so period, or latency, or throughput. There are many ways to do this kind of things. The frequently used model to describe the hardware, and so the target of the high-level synthesis, is usually the FSMD model. The FSMD model is very similar to what you have, for example, in a processor. So in a processor, you have a controlling part and you have a data path elaboration part, so a computing part. So this same model has been frequently used in many high-level synthesis approach. The idea is here not only to have a simple finite state machine, but an extended finite state machine where on the edge you may go from one state to another one, not only changing single bits of the output, but actually performing actions. And so you may actually update variable, you may compute something and store these results in other variable and so on and so forth. So this FSMD model, it's some sort of generalization of the FSM, so the finite state machine model, by adding on the FSM action on the edge. And the high-level synthesis usually try to build this FSMD in order to generate something that could be easily synthesized on a synchronous RTL description. Now, let's try to show in few slides how the high-level synthesis process works. So, as I said before, in the 90s, the starting description was VHDL. Now we usually start from an high-level code. The most common case is to use the C code. And here we have a very short example, quite synthetic. So you have a do while, a forward while, and you may have if and so on and so forth. So you have computation, and this computation is exploiting arithmetic operation, and this computation could be written in any way. So here you may have a simple assignment, and you may have assignment with a complex expression, calling function, whatever. Now, usually this description in high-level synthesis is managed by translating this input specification in something that a compiler may understand. So high-level synthesis leverage many things that have been introduced for a software compiler. So all the front end is actually sometimes quite the same of the standard software compiler. So you take as input the C specification, and you're going to build an intermediate representation. Quite frequently, the intermediate representation, as we will see later, is a contour flow graph. This contour flow graph tries to organize the computation in blocks. Those blocks are actually having a sequence of operation inside where the and these operations are not actually having relation inside the basic block. They haven't relation in terms of control precedence. So all the operations are actually having relation, and these relations are only related to the data dependencies that you may have between the operations. So in case there is no data dependency, this operation may run in parallel, for example. So understanding if an operation can run in parallel, it's pretty easy. It's just a matter to look to the basic block, which other operations are in the basic block, and see if there is dependency. So read after write kind of dependency. Another kind of things that the compiler is usually doing on the specification is to somehow simplify the description in a way that you have a simple assignment. So these simple assignments are usually named tree address form. So you have a destination variable and two or one input variable plus an operation on these two one input variables. So usually the compiler tries to reduce generic expression in unary or binary expression. Now, as you may see, the basic block is just one of the building blocks. Then you have a relation between the basic block, and this relation are usually the dependency, the control dependency between this basic block. And so And if you would like to say this in assembler, are nothing else than jump from one point to another point according to a given condition, if it is satisfied or not. And so this very simple example could be translated in this control flow graph. Once you have this data structure, it is going to start the actual synthesis. And here you have a zoom of basic block 3. So let's focus on basic block 3. And let's see what we are going to do with basic block 3. So the first things that we are going to understand is the order in which these operations are going to be executed. The idea is to execute this operation exploiting a controller, and this controller is not a generic controller able to execute any program as it happened for processor, but is a custom controller able to execute only this specific application. And in this controller, the state of this controller are actually describing which operation are going to start, which operation are going to end, which operation are going to be stalled till the completion of the execution. Here we have, let's try to zoom a bit. So here we have basic block 3, as you have seen. So since the multiplication takes more than one clock cycle, you are going to see that for each cycle, you are going to execute a different operation. And then in case the condition is true, you are going to repeat this state till this condition is true. Each of these boxes represent a state, so a cycles in the hardware implementation. So in order to understand how long it takes, you just have to understand how many states are traversed during the execution of your algorithm. Now, in this way, you know exactly when a given operation is executed, and this is computed by the scheduling, and there are many algorithms in order to define the order in which the operation are executed. And the order means that the operation, this multiplication will be executed after this operation. So the order, this edge you have in this FSM are somehow describing the relative order between the operation along the time. So, and once you have this, you are actually able to understand many more things in order to build the hardware. So the controller is just one part. The second part is building the data path. And the data path is actually built by instantiating register. So the model is reading the data from a register, starting from at the beginning of the clock cycles, do some computation, and then store the results in register. Again, this is very similar to the how the processor works, but in this specific case, we are going to build custom interconnection between the register and the resources implementing the operation. So during this previous phase and during the definition of the scheduling of the FSM, we have defined when a given operation starts. And so we know how long the variable are needed, so the lifetime of the variable. And so we may define which register is suitable for storing a given variable. So for example, this variable res1 is used only in this state, should be store the values till the starting of the next state. So this is the reason why we need a register, because from one state to the next one, we need to store the data in a register. Once we have used this register for storing res1 values, since the res1 values is not used outside of state 15, we may reuse the same variable for the same register for other variables. So for example, register 0 will be allocated to the output of this multiplication, since register res1 will not be used later in the in the design. So there is this things of reusing as much as possible the registers once the lifetime of a given variable ends, and so we do not need to keep the values of that variable. Once you know the mapping between the variables and the register, it starts to be possible to build the allocation and the binding of the modules on the operation. So here we have, for example, in state 15, a subtraction, 2 multiplication, 3 multiplication, and another subtraction. So 2 subtraction and 3 multiplication. So that means that all these operations are going to be executed all together. And so we need 3 multiplication in order to execute this multiplier. And we need 2 subtractor in order to implement these 2 subtraction operation. And then in this phase, so the model binding phase, you are going to do this association. So there is an association between the operation and the resource implementing this operation. And this is done for any states you have in the FSM. Now you know which component is implementing the operation. You know which register is storing the input variable of a given operation. So now you can build the interconnection. And the interconnection, consider, for example, the multiplier 0, is pretty simple. So you need to analyze all the possible states where this multiplier, so the component, has been used. And you need to look for each of these states. So for example, multiplier 0 have been used in state 15, state 16. And you need to look what happened in these 2 different states with respect to the read variable and variable that have been written by the operation. So you're going to see that you in the first state, you read from the input and from register 1. And in state 16, you're going to read from register 1 and register 2, and you're going to store the result in register 2. So you know the sources and the destination of the value. So in that way, you're going to add some interconnection logic that is actually able to steer the correct signals, the correct values along the given state. So for example, here we have an example, a portion of a data path plus a controller. And we implement the interconnection with multiplexer. So for multiplexer 0, here we have the input BR1, the input B in the state S15, the input R1 in the state S16. So in 2 different states, we have 2 different values. So the controller needs to send a signal, say, okay, when you are in a state as S15, it takes the input B and pass to the multiplier. When you are in state 16, takes the output of the register and pass to the input of the first input of the multiplier. Same things for the second input. And same things even for the output. Since here we have 2 output in 2 different states, and these 2 output goes in 2 different register, the controller enable the writing of one register 1 in state 15, and enable the writing of the register R2 when you are in state 16. This way, the computation is done by reading the value from the register or the inputs, doing the computation, writing the register on the output, and this is controlled by the FSM. And this FSM could go in different state according, for example, some input values that may came from the data. For example, the condition. And here you have, for example, what happened for case study 1, operation 24. And here you are the steering logic enable in case for the second operation. Think this kind of things happening for all the possible component instantiated and for all the states that you have in the FSM. Okay, so the controller required to define the scheduling of each operation for each basic blocks, and the scheduling define the set of states and the transition, and the output function depends on the results of the module and register binding. So how the interconnection have been built. So as you may see, there are many problems, each other correlated, that need to be sorted out. Usually these problems are solved one after the other, and the output of one problem will be used by the next one. So let's start, let's try to go a bit more in deep on which kind of intermediate representation we are going to use. The first thing is why we use intermediate representation. This concept is there since the 90s. And so the idea is to somehow split and try to keep separate the problem of describing the input according to a given language, and the problem to perform transformation and optimization of the intermediate representation. The idea is actually to keep those two things separated, because in that way you have part of the compiler that deals with the language and part of the compiler that is completely independent by the language. This concept is somehow
Hello. Is everybody here?
Yeah.
Oh, I mean, you dropped a little bit. Okay, just go ahead. Thank you.
Okay, that's fine. I hope that there is no problem with my internet connection. In case, please let me know. Okay, so the idea of the intermediate representation is to break the compiler into manageable pieces, isolate the front-end part from the middle end and the back-end part. So this part is actually pretty nice if it is independent by the language, because you may use the middle end part even for different language. This is going to happen for any existing compiler, and this has been recently bring to the extreme by adding further level of multiple level of intermediate representation. And it is possible to simplify the optimization of the compiler. So compiler is not only a translator, but is even an optimizer. So it takes the input intermediate representation and change the way the computation is done according to general rules or according to the target machine. There are many intermediate representation. So some are suitable for describing the syntax tree of a language. Some other are much more language dependent. So these, for example, describe the dependency of between the operation and in the graph. Some are more dedicated to the description of the control dependency between the operation. Some are more, I mean, the PDG is something that has been introduced for parallelizing compilers. So they try to remove as many control dependency as possible. And there are other descriptions like static single assignment form that simplify the work of the compiler in order to optimize and describe the representation. Free address code is something that I already mentioned before. So all the operation present in the initial specification will be somehow rewritten in a way that you are going to have only 2 input or 1 input operation. This simplifies even the high-level synthesis because it became much more simple to map the high-level operation on existing hardware. Same things is going to happen even with the instruction of a processor, because the instruction of a processor are going to have 1 or 2 input in most of the cases. And there are combinations. I'm going to, since I'm in 2 hours of class is not too much, so I'm going to focus on 2 things very important in the high-level synthesis. So the first thing is the basic block. So it's the smaller unit, and in this basic block, you are going to have the maximal sequence of instruction, assuming that in this sequence of instruction there is no label. So at least when there is only 1 at the beginning, and there is no jump in the sequence, but only 1 at the end. So you have a sequence of operation, and so the first one and the last one, and in between you may have operation, and this operation may be reordered without just looking to the data dependency, without looking to the control dependency. So this is actually a good kind of thing, so because it's reducing the complexity of the analysis, because the compiler just need to, for the control dependency, just need to look to the basic block, but not to the operation. And for the instruction parallelism, you do not need to look to the world specification, but you may focus only to the basic block instruction. And in that basic block instruction, understanding if 2 instructions can run in parallel, it's pretty simple because you are not having any control dependency there. Then, so you have, and so from the basic block, you usually build a data flow graph. And then you have the control dependency, because, I mean, in any specification, you have if, while, for, and so on and so forth. And so the control flow graph take care of the precedence related to the control between the operation, but it's actually not working with respect to the operation, but it's working with respect to the basic blocks. And basic blocks are the node of the control flow graph. So 2 operations I and j are in the same basic block if and only if the execution of I guarantee the execution of j. So you do not know when, but in case you are executing the basic block, you are going to execute all the operation in this basic block. And so in order to understand if a set of operations need to be started or not, you just need to look to the edge between the node in the control flow graph. There is a specific node that is named start entry node, where you are going to have the first instruction. Here you are going to see the example we have seen before. So now we may better understand what a control flow graph is. So the red arrow are the control edge. The basic block is a list of instruction. You have a label at the beginning, and you have a jump at the end of the basic block. And this jump is described here by a condition, and this condition say, okay, if the condition is true, you go through the true edge. In case the condition is false, you need to go to the false edge. With this simple description, you may describe any program. So whatever it is, the structure of the initial program, whatever it is the go-to, or whatever it is the language you are using, all those things are actually easy to map on the control flow graph, at least if we speak of a sequential program. In case we speak of a parallel program, the description need to be somehow enriched with other information. Another important thing is the static single assignment form. So any recent compiler is going to use this form. This form is been introduced in order to simplify the global optimization. and we are having the SSA form if in the program each variable is only assigned once. I mean, it seems much more complex than it is really. So, for example, if we have a sequence of instruction changing the generic program in an SSA form just means that each time you have an assignment, you give a version to that variable. So, for example, the first assignment to A became A1, and the second assignment to A became A2. Once you have gave the version of the variable, it became pretty easy to understand who depends on who. So, for example, before the next assignment of A, all the reference to A are A1. So, and same thing is, for example, for B2, so it's the second. So we assume that B1 has been somewhere defined, maybe is a parameter. So B2 is the second assignment. C1 is the same here. D1 is referring to B2, not to the input parameter we have B1. So in this way, it's pretty easy to understand the relation between the operation in terms of who defined the values and who is going to use that values. And in that way, it became pretty easy to discover the instruction level parallelism that you may have inside a basic block, because a basic block is nothing else than a sequence of operation. And once you have the SSA form, and it's pretty easy to build a data flow graph. And then once you have built the data flow graph, you are actually able to reorder, taking care that any true dependence between the operation is not broken. Okay. Okay, this is the easy part. What happens in case you have multiple basic block and, for example, you have an if condition, so controlling edge and complex control flow graph. So, for example, here we have an original program where A is assigned in the then and is even assigned in the else. So here we have two assignments. So which kind of naming we are going to have in SSA? So we may say, okay, this is the A version 1, and this is the A version 2. But then after this if then else, we have a use of variable A. And so the question is, which version this variable is going to use, A1 or A2? In order to solve this problem and keep the single assignment, the idea is to introduce an artificial operation, and this artificial operation is named phi, and this phi operation is nothing else. Okay, in case I came from this basic block where the variable is the latest version of variable A is assigned to A1. So, and in case we came from this side of the if, we are going to copy this A1 to A3. In case we came from the else, we are going to copy the A2 version to the A3. And then after this phi operation, all the operations are referring to A by using version 3. And that way, we still have a single assignment. We still be able to build a data flow graph easily, and so on and so forth. Data flow graph, as I said before, is built by starting by analyzing each basic block you have in the intermediate representation. It's a way to understand data dependency between the operation. And there are 4 types of data dependency. So read after write, write after read, and write after write, and read after read. I mean, read after read is not a big problem. So if you are going to read multiple times a variable, this is not creating any problem. For read after write, it means that some operation define a variable, and then the next operation is going to use that value. So those 2 operations cannot run in parallel, but need to be one need to follow the other one. for write after read and write after write, it's possible to remove the dependence between the operation by just doing some renaming of the variable, so changing the SSA, and in that way, the DFG is usually taking care only of read after write dependency. So here we have an example. So this example has been taken from the Micheli book, and it's a differential equation. So here you are going to have the equation used. This is the body of a loop. So here this body of the loop is executed till this condition is true. So sequence of operation, then you check the condition, and then you repeat or not the loop. Here you have in high-level language different way to describe. So you may have a binary operation, or you may have multiple operation put in a single expression. Then the compiler translates all of these in a simple operation. Each of these simple operation is described by a vertex in this data flow graph. And here you have the input of the vertex describing the input of the operation. The output is not even named because it's not important. It's just temporary variable that are used to feed the data to the next operation. And as you may see, the data flow graph, it's pretty useful in order to describe the dependency between the operation, the true dependency between the operation, and which kind of opportunity you have in order to reorder the operation according to the resources that you are going to have. Once you have this, you may build another data structure. Usually this data structure is named contour data flow graph. And this contour data flow graph is nothing else than the combination of the contour flow graph for between the basic block and the data flow graph for each basic block. All the compiler are using this kind of data structure. Okay, you have the data structure, you have the intermediate representation. Now you need to perform the scheduling. So the scheduling problem could be done in many different ways. The idea is to specify the order of the operation, as said before. Usually, the simple case is no restriction on the number of operations, on the number of components that you need to use in order to execute the operation. But the most common case is the resource constraint case, where you have a limited number of operations, limited number of ports in the memory, and then you need to organize and constrain the execution of the operation in a way that you are not going to use more than the given number of operations. And this is one of the possible problems. So resource constraint scheduling. There is another one that is time constraint scheduling. So you are constrained to complete the execution in a given number of cycles, and you would like to optimize the order of the operation in a way that you're not going to use more than a given number. You're going to use the minimum number of resources. So here the resource constraint, you're going to schedule the operation given some constraint, minimizing the latency. Here you're going to minimize the resource given as a constraint, the latency of the design. So scheduling definition is the assignment of the operation to time. So you are going to specify at which time a given operation is executing, considering a resource or timing constraint. The idea is to exploit as much as possible the parallelism, and this is done by using the data dependency, and try to exploit as much as possible the mutual exclusion. So if you're executing one basic block, you're not going to execute the operation belonging to another one. Try to exploit as much as possible the loops that you may have. We will see later that there are quite nice optimization that could be done for loops. And the scheduling affects the area, because we are going to choose how many concurrent operations, so how many resources we need to have in order to implement. So in terms of the processor, we are speaking of HALO, so how many HALO we are going to use in the design. And since we are dealing with the order of the operation, trying to exploit as much as possible the instruction parallelism, we are dealing to the concurrency of the resulting implementation. Scheduling, it's a quite complex problem. It has been studied for a quite long time. I mean, consider that the hardware design and the architectural design, the high-level synthesis is there since the 18. And so this means that there are many proposals try to solve exactly the same problem. The problem is an NPR, so there are exact solution, but these exact solution are not scaling very well. So there was many studies in order to define heuristics that try to solve the problem as fast as possible. Here you just have the list. The most known algorithm are ASAP, ALAP, list scheduling, integral linear programming, and the system of difference constraints. So, for example, the latest version of high-level synthesis, for example, from Xilinx is using this, but this algorithm is even used by other high-level synthesis tools. So what that kind of things means, we respect DFG. So let's start again from the differential equation coming from the D. Micheli book. We build a data flow graph. Once we build the data flow graph, the first scheduling that we may do on this is the ASAP scheduling. And the ASAP scheduling try to set for each operation a time where this operation will be executed. And this line represents the line where we start the we start the cycle of execution and we end the cycle of execution. So all these operations need to take the data and from a register or an input in these same cycles and need to write the outputs on a register before the next cycle is going to be executed. And in this way, here we assign all the operation, preserving the read after write dependency, because it's the only one that matters for correct execution. And in the approach followed by the ASAP is without limiting the resource, so is unbounded in terms of the number of resources. You are able to use as many resources as needed. And so you are going to execute as soon as possible the operation. So in this way, you are going to have this kind of effect. So all the operations start as soon as possible. There is a similar algorithm, but a dual one named ALAP, and is as late as possible. So the dual one, it's quite frequently used in order to solve latency constraint problem. It's actually pretty useful because it could be actually provide some metric like the mobility of an operation. If you look to this, for example, operation, this could be scheduled in this later step or could be scheduled in the first step. And so it means that this operation could be scheduled along all the way. So here or here or here. And so the difference between the ALAP and the ASAP is actually a good way to understand if an operation in terms of execution is constrained or not. And how much, which is the possible different step in which this operation could be scheduled. So resource constraint scheduling, it's the more complex problem. As I said before, it's the NP complete problem. The idea is there are two problems. Minimize the latency given the constraint in terms of area. So minimum latency resource constraint scheduling, or you have a dual problem where you are minimizing the resourcing, but the latency are constrained. There are exact solutions for these two problems, but there are even heuristics. For example, priority-based or list scheduling or the SDC are the ones that are usually used in order to solve the first one, the minimum latency resource constraint problem. keeping in mind that this scheduling means to have a different operation and different step. And in case we move from one step to the next one, we may reuse the resources. So the number of resources used depend on the maximum number of resources scheduled in the same control step. So the scheduling is going to define at least the number of resources used, the maximum number of resources used for a given type of operation. Then once you have this number, then you need to build the interconnection and so on and so forth, and bind the operation to the resource, but this is some sort of things that is feasible and could be done in a later step. Let's see the first scheduling, the most common one. So the list scheduling algorithm, it's based on a priority list where you are actually, each list is going to serve different resources, and the operation in queue in the priority list are in queue according their priority, and the priority could be defined in many different ways. You may range from force, you may have mobility. Recently, have been introduced the entropy, and so on and so forth. There are many different ways to order the operation in this list. And so once you put you put in this list all the operations that are ready to be executed, and the scheduler takes from that list the one with the higher priority, and then once it takes this this operation from this list with the higher priority, this is going to assign the control step and the resource that this operation is going to use. And this is done till all the resources in a given control step will be used. Once you're not going to have resources, you move to the next control step. And once you move to the next control step, you're going to restart from the beginning. And then the process is repeating with new operations that are being in queue because are now ready, because the data in front of them is ready, and so on and so forth. So here you are going to have an example, 2 multiplication, 1 addition, and 1 subtraction, and you're going to have this data flow graph with this different type of operations. So you start from this operation available. So you have as a ready list this list of multiplication, and so you schedule some of them. And since you have only 2 resources, you cannot accommodate all these multiplication on the 2 resources, and so you just schedule 2 of them. And you schedule the most critical one. Then once you have scheduled these 2 operations, the next subtraction operation became ready. You still have to schedule these 2 other operations, and so it means that in the next control step, the ready list became subtraction and 2 multiplication that have not been scheduled in the previous control step. And so you do repeat the process. So subtraction is available, multiplication is available because we have 2 multiplication. Again, in the next control step, we start to see other operation ready. So this subtraction, this addition, and so we have these 2 operations. Both of them could be scheduled, and so we move to the next step, and so on and so forth. So with this simple process, linear with respect to the number of operations you have in the data flow graph, you are actually able to schedule all the operations. Pretty simple, pretty easy to accommodate many things. So, for example, here we simplified quite much in the previous slide the problem. In real example, in real world, you're actually having operations that are not taking 1 clock cycle, but they may take fraction of the cycles. And so there are optimization that simplify the scheduling problem. I mean, they may create much more effective, efficient scheduling. So, for example, if you have very simple operation that takes a small fraction of the clock cycle, you may accommodate those 2 things, for example, in the same clock period. So for example, these two additions are very short with respect to the multiplication, so they can fit in a single clock cycle. And then you need to take care of operation that may take more, so multi-cycle operation. And you need to actually understand when an operation can start or not, when an operation can be chained with the previous one, and so on and so forth. So this problem is a bit more complex, and I've been addressed by work done by UCLA in 2006, and so they introduced the system of difference constraint. And this system of difference constraint is actually describing pretty well when an operation can be chained, when an operation need to stay in different clock cycles. So what they do is mainly look to the latency of each operation, look to the target cycle times, 5 nanoseconds, try to understand how long each chain could fit or not in a given cycle of 5 nanoseconds. So for example, this load cannot actually be scheduled in the same control step, because if you sum up all the time these operations are requiring, you cannot fit 5 nanoseconds. And this is described by this simple difference of constraint. Why this is pretty nice? Because it's actually able to easily describe the dependency constraint, the cycle time constraint, and later we will see that it's pretty easy even to describe constraint for loop pipelining. And in this way, you may actually able to build a scheduling that is exploiting chaining, is exploiting different latency, it's actually able to take care of pipeline and operation, and so on and so forth. So this algorithm is quite much generic, and it is actually pretty effective and pretty efficient in terms of time of execution, because the complexity of the system of different constraint problem, it's actually polynomial, because this problem does not need to be solved by a generic ILP solver, but could be solved by polynomial algorithm like Bellman and Ford. Pipelining. So next step is related to pipelining. So pipelining could be seen as in many different flavors. So you may have operator pipelining. So the single resource is actually able to take care in each control step of different data. So you may overlap on the same operation, different computation. So for example, a multiplication could be pipelined. So in each control step, you may start a new operation if the initiation time is equal to 1. You may have a function that are pipelined, so some sort of generalization of resource pipelining. You may have loop that are pipelined, and you may have a coarse grain level task in parallel that, besides going parallel, could be even pipelined. So there is no time to go through all the possible pipelining. Let's see only one of the most important problems that you need to address in scheduling, and this is the loop pipelining. So the loop pipelining is actually try to schedule not only the basic block, so this is the body of the loop, so this is the data flow graph that you may extract from the body of the loop. But if you actually schedule this operation, without, in a standard way, you are going to do first the load, then the multiplication that may take more than 1 cycles, and then the store. So this, for example, may take, if you schedule this operation of the body of the loop, may take 4 cycles. As we have seen before, once we have done the body of the loop, we move to the instruction of controlling the execution of the loop, and this may restart the execution of the body of the loop. So we may have, as standard scheduling, something that executes the first iteration, then once the first iteration have been completed, the execution, we start the next one. So 4 cycles times the n, the number of iterations. Pipelining is actually accelerating this execution, and this is possible anytime you are not going to have constraint on starting the next iteration of the loops, like in this case, because there are no dependency that prevent to start the next iteration. This is a dual loop, so it's a loop that all the iterations are independent from each other. So in this case, pipelining is trying to reuse exactly the same operation, but is going to restart the execution of the loop of or the next iteration, not waiting the completion of the first iteration, but just after one clock cycle. So the initiation time is the time that we need to wait before we start the second iteration of the loop. And if you count the number of cycles, in this case, it becomes more or less n times the initiation times minus something, there are some constants. So, I mean, the number iteration in this case move from n times 4 to n times 1. So you have a speed up of 4 times, more or less. So it's pretty important as optimization done on the loops. Another optimization, pretty relevant, is the loop unrolling. It's a transformation that replicates the loop body and times. And in that way, you may simplify and decrease the component latency because you are increasing the instruction level parallelism. And it's actually possible to increase the resource of the utilization because you are going to increase the level of parallelism. So you're going to have more instruction running in parallel. And so you're going to use better the resources that you have. Here is a very simple example. We have an original program, 32 cycles, 32 iteration, doing some sort of accumulation. Then we perform a partial unrolling. So we unroll once. So instead of I++, we have I plus equal 2. Here we have a new body of the loop. If we schedule this new body of the loops, we are able to exploit some further parallelism between these two iterations. So there is some overlap between operation done in the first cycles in first iteration and the operation that are done in the second iteration. As you may see, you may move from 32 times 4, so 128 cycles, to 96 cycles with this simple transformation. And you're not actually required to do anything than just intermediate transformation, intermediate level transformation. There are some issues. I mean, there are something that you need to take into account. This has been studied quite a long time ago. There was an analysis about the impact of the unroll factor and the latency. So you may decrease the latency of your application by unrolling, but this is not going always linearly in terms of reduction. You may have something that may create problem because of the unrolling factor. And another important thing is that if increasing the unroll factor means to have a more complex controller, and this actually means that the logic required to implement the controller became more complex, and so the latency of that part of the circuit is going to increase. So unrolling is fine, but you need to take care of this kind of effect. Other techniques that are important in high-level synthesis are, for example, code motion techniques. I'm referring to some techniques that have been proposed at the beginning of the 20. The idea of these techniques is to take the intermediate representation and try to move the operation from basic block to basic block. These techniques actually leverage some well-known techniques used by parallelizing compiler that try to change the order of the operation, anticipating some of the operation by doing code motion or by doing speculation. Speculation means that you may actually anticipate an operation that is and this, then you anticipate in this position. If you do before, you need actually to predicate this in order to avoid that the computation may, for example, wrongly write things that are not required. But doing this may actually improve quite much the performance of the application. So, for example, this is very simple example. So here we have this kind of control flow graph, and we have on the then we have only one plus, and we have an addition on the else followed by a multiplication. So the longest path, if we have this scheduling, is one cycle here, another cycle here. So the longest path is 3 cycles. If we do some conditional speculation, we may move, for example, the operation that we have in this control cycle and this position without actually changing the latency of basic block 1 and basic block 2. So we restructured the code, and we were able to improve the longest path by 1 clock cycles. These kind of things later have been studied in this paper. For example, in a way that this transformation have been done by exploiting a system of different constraint scheduling, and so those transformations are actually being addressed in a formal way that could be instead of trying and see what happened and so on and so forth. Other important things that is pretty relevant in parallel system is how to deal with pointers in an array. Synthesis of C models with pointer is actually something that have been starting to be addressed at the beginning of the 20th. Let's start with to try to understand which is the problem in this context. So in software, a program is actually targeting a virtual machine, and this virtual machine is having a memory in which all the data is stored. All the element in a program, in a software program, so all the variable, all the data in a software program, since it's mapped on the memory of this virtual machine, whatever it is, the machine that implemented the software program, is going to have an address. So each register each element of the memory is going to have an address. So it's pretty easy to take an address of an element that need to be stored in memory. And the notion of cache and memory page are transparent, but this is the most important kind of things that you have in software. In hardware, the concept of address is something that is somehow dependent by the application. So typically, the designer of the hardware are going to map the storage on specific data objects. So for example, you may have memories, but you may have register file, you may have register, and you may have something that may be just a single wire. So C in software and C in hardware are going to have some problem when you are going to consider pointers of this object. And so you need to somehow try to define a methodology that take care of pointer and how that pointer may need to be synthesized. So one way is the first approach that have been proposed for the synthesis of hardware is to somehow encode pointers, and so analyze the memory of the system and extract from the memory of the system and define for each element that need to be stored in memory, try to define some sort of address of that object. This address could be somehow a direct reference to the object, like a variable or array. Or in case you would like to have some sort of dynamic dereferencing, you need to somehow assign a code that describes the address of the object. So in that way, you may actually be able to understand if you are going to need one object or another one. So the idea, as it happened in software, it was to try to define addresses as encoding values, numbers, so somehow, and those numbers are used in order to dynamically solve the reference to the element in memory. Here we have an example. So for example, N will be mapped on register, but for example, this array will be mapped on memories. And for example, this struct been taken the address in this instruction, and then in these two instructions, we may refer to the field A or the field B, so different position in the memory. So this is usually a big problem for high-level synthesis, still this kind of idea, so how to encode the pointers. The best way is to try to remove as much as possible dynamic references. But I mean, sometimes in the real code, you may have this kind of problem. So one way, so the first approach, something that I've been proposed at the beginning of the 20, is to, okay, look to the code, see that pointer P may point to field A or field B, then collect all this may point to, and associate to any possible destination a value. So the first one is value 0, the second one is value 1. Once we know this, P is not anymore an address, but is values that refer to a position in the memory or not, or to another one. So for example, addressing the first field or addressing the second field could be replaced by assigned to P tag value 0 or value 1. So P tag means in case we refer to the first field, we are assigning 0. In case we refer to the second field, we assign 0. So P tag actually it's a very simple encoding of the destination of the pointer. And so this then will be used to change the rest of the code. So anytime I'm referring to P tag 0 and I would like to perform, for example, a load of pointer at the referencing of pointer P. So if P tag is 0, I'm actually replacing this star P with in.a. And I'm going to store the things. In case I'm referring to 1, I'm going to P star is going to be replaced by in B. Same things for the store. So we just actually put the two fields on the left side of the assignment. So in this way, you just need to rewrite the memory. We need to understand the reference done by the code in terms of pointers, what have been read and write. So we need to perform a point to analysis. And that way we may build a very simplified algorithm. Detail of this approach is actually described at least in 2 papers, but the first one that you may read is this Semeria de Micheli work published on TCAD in 2001. Sorry, 2001. There is another approach. Other tools are actually following this approach. Is not actually encoding anything, but is actually try to assign to each element addresses. So all as it happened in software. So in that way, the pointer are going to be stored in registers before. The only big thing is that you may have many bits in order to, but there are encoding approach that still work and that are different from the previous one. So any element will going to have an address. So it's you do not need to do any rewriting of the code. And so if you are going to perform a load, you just need to pass the address of the data, and then the size of the data, and then there is a component that put this data on the bus and takes and asks to the memory system if this data is there, and then return the output to the rest of the computation. Same things for the store. So we put the address, we put the value we would like to write, and then we put those things on the bus, and the bus will return, use these values in order to write the data in somewhere memory. In order to do this, it's actually a few lines of code. This is just an example of the component that may do both the load and the store. And with respect to the complexity, so you may expect that this way to do the things is more complex than the other one. Actually, it's very similar in some perspectives. So you need to actually organize the address not as a continuous addressing, but you may actually use some sort of sparse allocation. And for example, you may split the address space in two sets of bits. The set of bits that are referring to the offset inside an object, and the set of bits that are related to the object. So each object in the memory is going to have an ID, and this ID is going to use in the bus system in order to identify the object. So the memory is a distributed memory with some hole in between. But I mean, in this way, you are actually not able, you are not required to rewrite anything of the intermediate representation. You are going to have, you are going to leverage the standard bus system. And so you may actually perform any synthesis or any, you may synthesize any description with any kind of dereferencing. Double dereferencing is in this way is not anymore a problem. Another few details about how to organize the bus. The bus will be organized according to the call graph, and so in that way you're going to have buses that work on connecting each component. And so you, in general, you will have in each component the local operation, load and store, and this local operation will be connected to the bus. And this bus is actually connected even to the lower level bus that comes from lower level function. But since these functions are active in mutual exclusion with respect to the load store of this level, these kind of things may actually exploit quite well the bus architecture. Other things are related to the synthesis of pointers. So I've been proposed some techniques that are able to have pointers, so to synthesize pointers. Here is just an example where we have a pipeline of function doing different computation, and the execute is actually executing one of them according to the value you have in this array. The idea is pretty simple and have been explored in the past. It's to map each accelerator with an address. And so once you select one of these functions, you're actually putting on the bus the fact that you're asking for a given accelerator with a given address. You are going to write on the bus not only the fact that that function is going to start, but you're going to write the parameter assuming that each function is going to have an address for each parameters. And this is actually memory mapped kind of function that could be done. Then the sequence diagram for the function of indirect call is something like, okay, we call a function, putting on the bus the address of the functions by first sending the parameters, and then by sending the start of the computation. So these parameters are going to be sent directly to the function that need to start, according to, and then the function know who is calling. So during the communication of the indirect call, we not only send the activation, but we send who is calling. So the notify from the callee will be put on the bus as well and sent back to the caller. And so the caller then could be able to read back the values from the memory. So in that way, you may call any function just putting the right address of the function. Coarse-grained parallelism. Coarse-grained parallelism, there are many different parallelisms that you may synthesize in high-level synthesis. One of the first possible optimization is try to exploit loops that are completely parallel. So all the iteration can be executed in parallel. And there are a number of iterations that may actually not be known in time. And there are many different ways to execute this. So you may have two components doing half of the iteration in the first one, and the second half of the iteration to the second one. You may actually exploit pipelining, as you have seen before. There are even techniques that try to do the vectorization and synthesize the vectorization of the instruction. That means that the controller is going to execute multiple instructions at the same time. So the FSM is quite simple in this case with respect to the other one, for example. Big problem is, I mean, in case you have a single nested loop, that's not a big problem. In case you have outer loop, so loop inside outer loop, there are possible approach that do loop vectorization. So for example, here we have the outer loop that is a dual loop. So we may have two loops running in parallel. And these two, if the number of iteration of, for example, of the inner loop is the same, we may actually vectorize the instruction in this way. And so we may execute this instruction one after the other, but using a single controller, not two controllers running in parallel, sharing the instruction. So outer loop vectorization constraint, you need to have a dual loop. You may have multiple levels of parallelism. You may have nested, so nested condition could be considered, but usually in order to deal with this is to predicate the instructions, to translate the if in some sort of predication. And since the number of iterations may depend on some values, so you need to find a way to understand if a given operation need to be executed or not according to the end of the loop. This have been explored in high-level synthesis. So vectorization creates simple finite state machine. You need to have a very simple access. You may use vectorized instruction, or you may replicate scalar function units. So instead of having a vectorized component, you may actually have multiple instructions. The disadvantages is that you need to have more complex functional units, and you may need to have larger, much more complex memory infrastructure. Here is, for example, a design flow. So analyze the intermediate representation, and then once you have analyzed the intermediate representation, do classification of the instruction, transformation of the instruction, and then the synthesis. Here is just an example. So here you have, we use OpenMP SIMD in order to describe a dual loop. We have two nested loop, and we have if condition, and we have a memory access. So the first thing is the pre-processing. Once you have done this, you annotated the instruction in different ways. So here you recognize that these two instructions are going to be executed under this condition, and this instruction on the opposite one. So this instruction could be predicated, and it could be, some of them could be vectorized. So the red one are vectorized. The blue one are multiple scalar instruction, and you have in yellow the dual loop instruction and the nested loop instruction. Once you have transformed this, you build the predicated version by instrumenting. So here you're going to see, for example, two instructions dealing with two different parts of the array with different predicate. This is a vectorized instruction, so each operation is predicated by this condition, and so on and so forth. And vectorized instruction could be fully parallel, so 4 units doing the same things at the same time, very fast, larger area, could be pipelined, good performance, more complex design, but less resources, or one after the other. So complete reuse of the resources, but with worst performance. Another possible approach is to parallelize coarse grain on starting from the loop body. We consider this, it has been considered this quite recently because coarse grain parallelism is pretty important to manage for. And so we have, for example, see this problem when we have irregular application, and this, for example, have been considered for the acceleration of the query of that we would like to accelerate on hardware. So there is some part of the framework that deals with the extraction of this query, describing this in C, C++, and then this could be executed by the system software or could be translated in hardware by performing the high-level synthesis. Here is an example of a query. It's a query based on pattern matching. And these queries are irregular because they are working on graph, but they are highly parallel. So we developed, for example, one of the approach could be to develop a dynamic scheduling controller. So a controller that starts the operation and once the data are ready. This is different with respect to the FSM approach, where you statically schedule the operation in a given time. So here the approach is to start the execution once you have the data. This parallel controller design requires some module that check if the data is ready or not, the availability of the resources, or in case there are failure, the restarting of a given operation. The idea is to actually have something that perform dynamic scheduling along the computation. And this could be relevant anytime you have variable latency in the system. So for example, on the left, you have a data flow graph, and this data flow graph will be mapped on different operation. And these different operations are managed by an execution manager. And this execution manager dynamically asks to the data path to access the resources. And all these kind of things actually does not have a real FSM controller, but is much more a distributed array controller. This is actually pretty useful because it allows speculative operation, variable latency memory, function call. It could actually accommodate a variable latency hardware AP. There is the possibility to have dynamic reordering basing the scheduling of the operation during the execution of the application. There is some sort of self-adaptiveness since if the latency of a component change, the algorithm self-adapt. And the complexity is a bit more than the FSM. So you're going to increase the size of the controller, but you're going to have something that is much more dynamic. This is possible because we are considering a hierarchical approach. So you are going to have for example, in this call graph, you're going to have an hierarchy of component and a bus that actually could be arbitrated. And this is pretty fine in case you have algorithms that are going to have dynamicity and irregularity in terms of the memory access. These have been experimented in order to support the execution of operation in a dynamic way. For example, when you have OpenMP4, you may have dynamic in the directive of the OpenMP4. So that means that you are going to have physics accelerator that could be started, but could be reused for different purpose and could be actually activated dynamically by a task dispatcher. This has been found very efficient when we synthesize graph-based algorithm. If you like, you may see this paper. On top of that, another kind of things that have been studied is to, for example, add not only the dynamic patching of tasks, but it is to try to reuse task by anytime you have an access to something that is blocking, like a read from the memory, we introduce something like context switching. So the task, the kernel, the component implementing the kernel asks for a data to the memory, and then since the data will not come back instantly, we stop the execution of that task, we perform the context switching, doing some changing of the hardware, and then we restart with another task from the task dispatcher. So this is pretty useful because it's exploiting, it is able to hide the latency with, and in case you have highly irregular application, and it's exploiting the dynamicity of the system. Here there are some further details on how the OpenMP will be mapped on the architectural and how the context switch is performed by the single unit. Few things more. Those kind of things could be relevant for the students. There is an open source that implements most of the things that I have presented. The framework is in open source. It's available from those links. It's GPL version 3. Is supporting GCC and Clang. So it's actually able to support a different compiler. It's actually able to implement all the things that you have seen, and is actually able to target many different backend from many different FPGA vendor, but is even able to support, for example, Open Road. Here there are some links for downloading the binary distribution, but if you like, you may compile by yourself, going directly to the source on GitHub. There is even some further material. We did in the past some tutorial on this stuff, and so there is a collab where you may try without actually downloading or compiling anything, all the things that we have discussed before. That's it for the first part. Let's move to the second part of the presentation. As I said before, I'm going to present in B alpha Antonino Tomeo. Just a second. So this part is much more related to high-level compiler and SODA. So here it's few slides introducing the problem. So here we have as a problem, not anymore a C description, but something that today is it seems to be very relevant. So many data scientists start to use technology like FPGA or ASIC, and so they would like to try to accelerate high-level application. And here, a high-level application means application written in Python. So if you go through software, that means that you have a library and runtime framework or a framework optimizing this Python application that are able to generate binary files. And that binary files are actually then executed on the CPU or GPU, it depends on the target machine that you are considering, or the TPU. Now, the idea this set of slides is to show that it's even possible, and we will see how, to do this path for FPGA or ASIC. And so we need to find a way to translate high-level Python language, high-level language, maybe in Python, in something like HDL Verilog. So what this kind of things means in terms of a compilation. I mean, very similar to the A-level syntax, but taken to an higher level. So here we have a source program written in C. As we have seen, this program is compiled and compiled by a compiler like Clang in this case. And the C is then translated in instruction that depends on the target machine. Now, compilation is so not only a matter of translation, but it's a matter of optimization. So you would like to have the best program for the given target architecture. You would like to have this at maximum speed, so you don't want to spend too much in the compilation, and you would like to have correct code by and the code that you wrote should be implemented in a correct way, preserving the meaning, but you would like to have the maximum speed for that code. Checking if the description is correctly written, and so on and so forth. So modularity, extensibility, and correctness of the intermediate representation are pretty important. You would like to reuse as much as possible the optimization done done before for other architecture. So maybe you would like to try to exploit as much as possible all the target independent optimization. And then for a given targeting architecture, you would like to generate the hardware. So this kind of things is usually done by compiler. Just a second. By splitting the compilation in different parts. So one part is dealing with the front-end part. One part is working on intermediate representation that is completely independent by the initial language. And then there is a part that is usually the backend that try to optimize the intermediate representation in a way that fit the target architecture, trying to get the most from the code with respect to the target hardware. Now, this is the standard compilation flow. So, but there are many languages. So you're going to have many different front end that those kind of things is going to increase. And here we just have CUDA, OpenCLC that are going to use more or less the same front end. Java is using a different front end. Swift is using another front end. Flang is using another front end. So Fortran is using another front end. So there is this problem that you may have many different front end. And each of them is actually managed in a completely different way. So you would like to have something that maybe is still having some high-level information, but could be reused from language to language. So again, we may try to have details about the language described by the ST, so Java, or C or CIL, they are going to have the part related to the language separated from the rest. But it would be nice to keep some high-level information before getting down to the lower level encoding in Ellen, for example, in the one that is usually used by the compiler, and try to do some transformation that preserve that are actually more abstract and so much more easy to be managed by high-level optimization step. So this kind of things have been somehow proposed quite recently. So the idea is to have a source program that actually is compiled and then translated. And this program could be anything. So it could be even Python DNN, deep neural network models. And deep neural network models could be actually describe a different level of abstraction. So you may have a very high level where you have a TensorFlow operator, and then this will be translated lowering down to the target architecture. So this stack of different dialect is actually what has been introduced by Christian Lochner with MLIR. So MLIR is actually a way to deal with the different possible dialect you may have in a compiler when you start from very high level description. This DNN is just an example, but the same things actually is going to happen even for other possible input to the compilation flow. So MLIR start to be something that try to raise the level of abstraction for the target independent optimization, reducing the size of the intermediate representation and using things that actually are much more high level. So here we are going to see an example where we have an high-level description. So you take two parameters, and then you have this computation that will be passed through. And so the idea is if you are going to define a step for a given language that is based on this high-level dialect, you may reuse even for other language. Here is an example in Python. So this is a very simple ML Python model where you take this forward function, and then this forward function could be translated in a dialect. So there is this translation part in MLIR that translates this in TOSA. TOSA is a very high level. So as you may see, here you are going to see transpose, reshape, matrix multiplication, and then clamping, so ReLU kind of operation. So all these kind of things are going to describe a very simple machine learning model. So each of these is actually a function taking input and producing output. So the idea is to do some transformation that are possible at that level, then on each of these components, try to lower the level of abstraction down to, for example, dialect that are suitable to manipulate linear algebra description. This is just an example of this translation. And then once you have done that transformation, you may actually would like to move down again, try to understand better the content flow, the parallelization of this small function, and so on and so forth. So each level, each dialect are going to have the associated transformation, and those transformations are actually requiring to have to be suitable for the given dialect. And then the idea is to reuse all this transformation for in order to improve the code. Here you have an example of transformation, and this is the loop tiling. As you may see, loop tiling became pretty easy to implement on a dialect like this one. It is much more easy than and easier than the case of LLVM. And this is another example, loop unrolling. Again, all those kind of things are available in the MLIR framework. So unrolling the loop at higher level just means to actually repeat the code many times. But with respect to lower level, the operator are not anymore single variable or single pointers, but are much more generic, like tensors, so vectors of data. And each of these could be somehow work on more complex operations. So analysis of the dependency between the load and store became much more easy. Understanding if a loop is parallelizable or not became much more simple because you are going to work on a simplified description, but not losing the important information there. Other kind of transformation that could be done is, for example, scalar replacement of aggregates. So trying to remove as much as possible the vector of data. Anytime this is doable, could be done. And all these kind of transformation are, for example, pretty important. For example, in R, here is another transformation that takes this SCS dialect and translate in a new dialect, a dialect that has been defined for OpenMP. So since it's easy to understand, look into the data dependence between the operation we have in this dialect, it's easy to understand that this is parallel. So parallelization became easy because you may actually even exploit polyhedral analysis in this domain. And so you are actually able to then translate this, for example, in an OpenMP dialect. So we have seen that recently compilers have been somehow improved by adding further level of abstraction. So we have seen for the high-level synthesis, the abstraction of the intermediate representation is pretty low. So you have operation, you have statement, simple statement, you have control statement, you have goto, and so on and so forth. Here, the recent development of compiler are starting to consider higher construct, higher level construct, not only single operation, but operation on vector, operation on tensor, explicit description of loop, nested loop, so transformation like loop unrolling, and parallelization become much more easier. So our problem, as we have seen, we have a domain scientist describing the things in domain-specific language, and would like to use a framework that translates this maybe in an FPGA version, so accelerated by exploiting technology like FPGA, building their own tensor processor, for example. So how we do these kind of things? One approach in the past was more or less similar to the Ninja programmer. So the Ninja programmer know everything of the final architecture, takes the input from the specialist and write everything in hardware description language. But this kind of things is quite costly, takes quite much time. It's having, you are actually not be able to do much in terms of design space exploration because implementing just one thing takes quite a long time. So you're actually able to implement just few solutions in order to see which is the best one. So who is doing this need to be very smart in order to choose the right answer to the acceleration of a given specification. Another possible approach that is starting to be used is to start from the domain-specific language, use high-level framework like TensorFlow, PyTorch, whatever, pass these things to the HLS developer, and then the HLS developer usually start from a C description generated by those high-level framework, annotate the C code, and then use high-level synthesis tool as we have seen before. And then you're going to generate the HDL file. So let me. And then you are implementing all this on an FPGA and ASIC. This is fine, but it is possible to do something more than that. So you may, just a sec. Okay. So it is possible to do all those steps by using a compiler-based front-end. Here is just an example, SolidOpt. SolidOpt is starting from MLIR, is performing transformation on MLIR, and all the transformation have been studied and developed in order to be suitable for the hardware design. Then it's going to generate an intermediate representation still in the intermediate representation used by the compiler, so the .ll or the LLVM intermediate representation passed to Bamboo. Bamboo is an open source tool we mentioned before. that is based on clan. And so it is possible to perform and accept this intermediate representation and generate hardware and FPGA and ASIC. And we do this more or less in automatic way. And so this means that we are able to perform quite extensively design space exploration. Here we may see the more detail about the SODOPT design framework. So high-level framework based on TensorFlow PyTorch, generate the MLIR intermediate representation. Then SODOPT partition and optimize the intermediate representation by performing some standard MLIR transformation, plus some recipes that are much more suitable for the high-level synthesis, for the hardware design. And it's possible to do this kind of things by iterating along the way, repeating all these things, and in a way that are actually allow a better design space exploration. Okay, and these are all the steps that we have till the backend. Here we have an example of possible front-end optimization for high-level synthesis. So, for example, tiling and unrolling are considered because they are creating and they are improving the creating parallelism. They are improving the performance of the application by increasing the instruction level parallelism. Other possible things that could be done is, for example, working on the memory, on the allocation of the buffer, on the partition of the memory in order to reduce the access to the memory and making this parallel and efficient once you go to the FPGA side. Other transformation are try to remove redundant code, try to reuse results that have been previously created without actually storing this in memory, and so going through the whole stack of the memory, and remove that code, common sub-expression eliminations. So all those kind of things are going to reduce the complexity of the hardware, and this could be done by SODOPT. So the answer to the first question about the high-level optimization down to the hardware could be described by these 6 steps. So you work with Python, describe your application, then you use so you are going to use all the high-level framework that are possible, so PyTorch or TensorFlow. Then you translate these within that tools in MLIR. You do some optimization on this generic one, then you translate you do some optimization with SODOPT, and then you translate in something that could be understood by an high-level synthesis tool like Bamboo, and so you're going to generate LLVM description. Then the high-level synthesis tool generate the Verilog file, and those Verilog file could be implemented, for example, in ASIC by using an open source logic synthesis framework named OpenRoad. And you get the GDS2 files ready for the ASIC implementation. There are further detail along these links about how to do this with Soda, Bamboo, and OpenRoad. Some benchmarking. So here we take the Polybench as example, and we compare this, for example, with other state-of-the-art. So in green, you have SODOPT plus Bamboo for FPGA, and in red, you have SODOPT plus Bamboo for ASIC. So as you may see, you may have quite a large speed up with respect to doing the same things, just passing the lowering of the high-level intermediate representation without any optimization done by SODA-opt to the high-level synthesis tool. We did even some comparison with other approach like Scale HLS plus Vivado. We have tried our tool, so the SODA-opt plus Vitis or SODA-opt plus Bamboo, and as you may see, sometimes Scale HLS plus Vivado that did better and sometimes worse. Here is some detail about the related work about high-level synthesis. So higher level synthesis, so the synthesis starting from Python. And the approach we are actually proposing with SODA synthesizer, SODA and plus Bamboo is actually able to cover all the steps, all the functionality we have described in this box. So it is possible to perform optimization without doing any manual annotation. It is possible to automatic partitioning the code. It is possible to perform design space exploration or and consider optimization strategy specific to FPGA or ASIC, and it is going to support FPGA and ASIC. So all the TIC are there for a SODA synthesizer, not all the TIC are there for other approaches. So in conclusion, MLIR starts to enable higher level optimization. It starts to improve the support, I mean, the optimization of specification that are usually written by domain specific expert. And the framework is actually being exploited by our two groups in order to improve the hardware accelerator synthesis, both considering the FPGA or the ASIC. And we saw that there is quite much improvement in terms of possible speed up that you may have considering something that has not been optimized with our tools. So in that way, we are actually end-to-end to actually help the high-level, the domain expert to control a complex tool chain like the one that you have saw. And so we may start to speak about agile hardware design. That's all. I think that I should be in time. Not sure that there are questions. I hope that the recording will be fine. Here are further links to SODA-opt in case you are further interested. In the chat, you may find the link to the PDF I just presented. In case you would like to interact with us, I mean, we are pleased to have collaboration with other groups, both us and both PNN and people. I'm starting to be begged by my cat and would like to enter in the room. So I think that we can stop the recording. I don't see any questions, so I'm supposing, in case there are questions, just send me an email. Thank you to everyone. I'm going to leave the chat. In case you need just something, need something, just contact me by email.